potential, what do you think of? Like if I say to all of you, you have the potential to be outstanding nurses. The ability, right? You have the resources. Well, membrane potential means that that membrane has stored energy, and that's the potential. So a membrane has stored energy, and it has the potential to become engaged or to have an action potential. And that's what we're going to be talking about today. So a membrane can either be at rest or it can be excited. So the first thing we're going to think of, everyone saying this?
Oh, I did.
The first thing we're going to talk about is a resting membrane potential. So what do you think that is? Resting membrane potential.
It's not active.
Yes, it means the membrane is at rest, but it has the potential to become engaged. Okay. So membrane potential is a slight excess of positively charged ions on the outside of the membrane, and a slight deficiency of positively charged ions on the inside of the membrane. Okay? So in your notes, you want to make this simple, okay? So in your notes, you want to put during a resting membrane potential, the outside will be slightly more positive than the inside. During a resting membrane potential, the outside will be slightly more positive than the inside. Or you could say the inside is slightly more negative than the outside. And I'm only saying this to you because students get confused. It, really depends on the wording on the exam, okay? So a resting membrane potential is going to be slightly more negative on the inside of the cell. Neurons are remarkable among cells because they initiate and conduct electrical signals called nerve impulses. So in your notes, you could put another name for action potentials are nerve impulses. Nerve impulses. A nerve impulse can be described as a wave of electrical fluctuation that travels along the plasma membrane. All living cells maintain a difference in the concentration of ions across their membranes. And again, as I just said earlier, difference in electrical charge is called a potential because it is a type of stored energy. A polarized membrane is a membrane that has membrane potential. Okay, it's not quite engaged yet, but it has that membrane potential. The magnitude of potential difference between the two sides of a polarized membrane is measured in volts or millivolts. The sign of the membrane's voltage indicates the charge on the inside surface of a polarized membrane. So all I want you to try to remember here is that when the membrane is at rest, it typically is going to be about negative 70 millivolts. Negative 70 millivolts. And as long as we have slightly more positive ions on the outside and slightly negative on the inside, that membrane will remain at rest. Okay? So it's going to be slightly more positive on the outside compared to the inside of the membrane. So, and here, the slight excess of positive ions on the membrane's outer surface is produced by ion transport mechanisms and the membrane's permeability characteristics. What does it mean when I say, if I say that water is permeable? What do I mean by that? Yeah, it can cross, right? It can easily cross through that lipid bilayer. So the membrane's selective permeability characteristics help maintain a slight excess of positive ions on the outside of the surface membrane. So what that's telling you is that only certain ions will be allowed to come through, because it says it's selectively permeable, right? So it's only going to allow certain things through. The permeability characteristic of each cell's plasma membrane are determined in part by the presence of the specific membrane transport channels. Many of these channels are gated channels. So when they're gated, they're only going to allow specific molecules to diffuse across the membrane. And it only happens when the gate of each channel is open. Okay, I know that's a lot of verbiage, right? Okay, let's look at a nice visual. Okay, I think this is going to help you. So this is a resting membrane potential. If you look at the top in blue, this is the exterior of the cell, or the outside of the cell. Here, on the bottom in orange, is the inside of the cell. Okay, you okay so far? All right. These little guys here are the channels. So you have the red and the lime green channels, and again another red channel. So what do we know about a resting membrane potential? The outside has to be what? Slightly more positive than the inside. Now this is where students get a little confused, because both ions that we're going to talk about are positively charged. So it's a little confusing, right? So sodium is positively charged, and so is potassium. But here's what's going to happen. So you have all these sodium ions here on the outside of the cell, and you have potassium ions on the inside. Now let's look at the first channel. It's a potassium channel, and it's open, right? So potassium, during a resting membrane potential, can pretty much move freely, right? You see how it's open? So it can go from the inside to the outside. Let's look at the next two channels. These are sodium channels. Now what's happening? They're closed. So sodium it can't move freely, right? So the sodium that's up here in the exterior, it can't go down inside the cell. So because of that, we're going to have just a slight positive ion concentration on the outside of the cell compared to the inside. And as long as we have that slight difference, the membrane will remain at rest. Does that make sense? It has the ability to become engaged. But as long as it stays like this, that membrane will stay at rest. Now, without me going any further, what do you think would have to happen for us to have an action potential? An action potential is the opposite of the membrane being at rest. Now it's engaged. What do you think would have to happen with these ions? I'm sorry?
They have to both be equal?
You're thinking, guy, that you're on the right track. What's going to happen, you see these sodium channels? They're gonna open up. And then we're going to have an influx of the sodium inside the cell, or inside the membrane. So now what's going to happen? Now the inside is going to be more positive than the outside. And that's when we're gonna have that action potential. Does that make sense? We're gonna go into, I'll go over it again. But I wanted you to kind of think, okay, well, if this is resting membrane, what's going to happen with an action potential? So just think, these channels are gonna open up, these sodium ions are going to rush in, and now the inside is going to be more positive than the outside. And that's going to cause that action potential.
What makes them open up? Is the overloading?
Very good question. Any type of stimulus, right? Let's say that this was a grill, okay? And I'm grilling hamburgers. And I'm not very good at it, and I burn them, okay? What's going to happen? When I burn the hamburger, what are we gonna see? We're gonna see smoke, right? That smoke would be the stimulus. And so when we have that stimulus, it's going to open up the door, which in this case is going to be the sodium gated channel, right? So it opens up, and what do we have come in? Lots of sodium. We're gonna have that influx of sodium. And now the membrane is engaged. Do you remember on Tuesday when we talked about the neurotransmitters and how they're activated, they come into they're carried in by little vesicles? Well, this is kind of what we're talking about here. And then we're going, if the neuron senses that we should respond, then it's going to carry that signal down the axon, and we're going to have that. Does that make sense? Okay. Mm-hmm. So, again, sodium, potassium ions, and remember, you want to start knowing, and you probably already know this from chemistry, but potassium, if you look at your chart, it's a K, okay? So potassium, K, that is for potassium. What's for sodium? Na. Excellent. So the potassium channels are open in the resting membrane, allowing potassium to diffuse down its concentration gradient. What does that tell you, my nurses? If it's going down the concentration gradient, what is it? Is it active or passive? It's passive. And thus adds the excess of positive ions on the outer surface of the membrane. And that's what we see right here. Potassium membrane is open, and it's going to keep that exterior more positive than the inside. So remember when we talked about muscle contractions last semester, remember that? And we talked about active transport, and I said for right now, all I want you to remember about active transport is that it uses pumps. Remember me saying that? Okay. Remember I said we revisit those pumps? Well, this is the day. We're going to revisit these pumps. So active transport mechanism in plasma membrane that transports sodium and potassium in opposite directions at different rates. These pumps maintains an imbalance in the distribution of positive ions, and as a result, the inside surface becomes slightly negative with respect to the outer surface. Or we could say the outer surface is slightly more positive than the inside. The sodium-potassium pump moves 3 sodium ions out of the neuron for every 2 potassium ions it moves into it. So my nurses, that is a 3-to-2 ratio. A 3-to-2 ratio. 3 sodium ions in for every 2 potassium ions that are, 3 sodium ions out for every 2 potassium ions that are moved into the cell. So by doing that, it keeps it slightly more positive on the outside because it's a 3-to-2 ratio. 3 positive ions, which are the sodium, are going outside the cell for every 2 potassium that goes into the cell. Are we okay with this? Are you sure? So if I asked you on the test, let's pretend that it was an essay question, and it's not, but let's just pretend it is. And I ask you, what keeps the membrane at rest? How would you start out by saying, what would you say? What would you write down? Good, that it's slightly more positive on the outside than the inside. And why? What keeps it that way? The sodium-potassium pumps, yes, and the ratio, right? So it's a 3-to-2 ratio. So you would write down for every 3 sodium ions that are going out of the cell, 2 potassium ions are going into the cell. That's your 3-to-2 ratio. And it's just that slight imbalance that's going to keep the membrane at rest until we have a stimuli that's going to activate it, like me burning the hamburgers, right, and the smoke. So here's a nice little visual of what we just said. Here's your sodium-potassium pump. Remember, it's active transport, so it requires ATP. It requires energy. So up here, we just have simple diffusion. right? They're going down the concentration gradient, there's no ATP involved. But with this sodium potassium pump, now we have to have ATP, because we're going to take 2 potassium, it's gonna go to the inside, and 3 sodium are gonna go to the outside. And that's gonna keep that membrane at rest. That make sense? We're good? Okay. So the mechanism in the plasma membrane actively pumps sodium out of the neuron and potassium into the neuron at an unequal rate of 3 to 2 ratio. Because very little sodium re-enters the cell by diffusion, this maintains an imbalance in the distribution of ions and thus the resting membrane potential. It's all about that 3 to 2 ratio and those sodium potassium pumps. You good so far? Okay. Let's see how these action potentials get started. The first thing that has to happen is that we have to have a local potential. And I want you to know the definition of a local potential. It is a slight shift away from the resting membrane in a specific region of the plasma membrane. So excitation. It occurs when a stimulus triggers the opening of additional sodium channels, allowing the membrane potential to move towards 0. Okay, remember at rest, it's negative 70 millivolts. So the closer it gets to 0, we're going to have what we call depolarization. And I want you to put in your notes, depolarization is action potential. That's when you're gonna have that, the firing of the neurons. Okay, depolarization, action potential. You also wanna put in your notes that repolarization, you wanna think of relaxation. And they both start with R, so you can't mess this up, right? Okay, repolarization equals relaxation. I'm not gonna go into it right now because we're not there yet, but repolarization and depolarization are huge when we're talking about what? Do you know? Has to do with the heart. EKGs. EKGs. What's an EKG? It measures the electroconductivity of the heart. So, right here, right, we're going to, when we start talking about EKGs, I'm going to be revisiting depolarization and repolarization. So I want you to commit to your memory forever. Depolarization, action potential. Repolarization, relaxation. Okay, if you can remember those 2 things, when we get the cardio and we go over EKGs, it's going to be a lot easier for you, okay? Because we're going to talk about what each wave means on the EKG. Okay? All right. Let's see. Inhibition. What's inhibition mean? Yeah, to stop. So it occurs when a stimulus triggers the opening of additional potassium channels, increasing the membrane potential. So this is hyperpolarization. So during this time, it's very unlikely that we're going to have an action potential. Okay, because we got additional potassium channels opening. Local potentials are called graded potentials because the magnitude of deviation from the resting membrane potential is proportional to the magnitude of the stimulus. So they're called graded potentials. So I already told you that an action potential is known as a nerve impulse. I want you to also commit that to your memory. Sometimes during an exam, they may not say action potential, they may just say nerve impulse. So I want you to know both. So the mechanism that produces the action potential. When we have an adequate stimulus, it's going to trigger the sodium-gated channels to open up. And when they open up, we're going to have an influx of sodium coming into the cell. That is going to cause a local depolarization. Now the inside of the cell is more positive than the outside. As the threshold potential is reached, voltage-gated channels open and even more sodium comes in. This causes further depolarization. Any questions so far? I don't know if your silence means you understand or it means I have no idea what she's talking about.
It's a lot.
I know it is. I know. The action potential is the membrane potential of a neuron that is conducting an impulse. So the threshold potential is the minimum magnitude, a voltage fluctuation that the summation or conduction zone, do you remember what the conduction zone is? So the conduction zone is where we're going to have what? An action, right? Something's going to happen. It's called the conduction zone. So it must have to trigger the opening of a voltage-gated ion channel. Okay, so let's back up a little bit from Tuesday's lecture. We have the input zone, right? What's the input zone? That's where the neuron, it's receiving the information, right? Input zone. And then we have the summation zone. What happens in that zone? Yeah, it's going to sum up that information that was just received and figure out whether to respond or not. If it decides to respond, then it's going to send that signal further down the neuron, or the axon, so that we can have an action potential. And that summation zone, what's in it? It's called the axon hillock, right? The axon hillock is what's responsible for summing up all that information and deciding whether it's going to respond or not. And the conduction zone is where we're going to have the response. This is another visual that's, basically showing you the same thing at rest. And they did this for simplicity, but you have all the sodium ions on the outside and the potassium on the inside. Okay? Showing you that at rest, the outside of the membrane is slightly more positive. Depolarization, now look what's happening, those sodium ions are going inside the cell. Okay, we have an influx of sodium. And then repolarization, things are relaxing now, they're going back to the resting membrane potential. So now what we see is that those sodium ions are going to move to the outside and the potassium are going to be moving into the inside, so they'll change positions. Okay. So again, as more sodium rushes into the cell, the membrane moves rapidly toward and continues in a positive direction to the peak of the action potential. After that action potential peaks, then the membrane begins to move back towards the resting membrane potential, when the potassium channels will open again, allowing the outward diffusion of potassium, and this is a process known as repolarization or relaxation. So voltage-gated sodium channels stay open for only about 1 millisecond before they automatically close. I mean, it's kind of hard to fathom that, right? That it only lasts 1 millisecond. The action potential is a all or none process. I want you to highlight that in your notes. It is a all or none process. Can everyone see my dominoes up here? Can y'all see those? Okay. So what I mean by an all or none process is the once my finger hits the domino, they all fall. That, it's the same way with an action potential. The once we have that action, you can't stop it. It's going to go, and it only goes in one direction, right? So it's an all or none process, and it's not reversible. All or none. One direction, it's not in reverse. Okay, please remember that. So a brief hyperpolarization occurs, and then the resting membrane potential is restored by the sodium-potassium pumps. Okay, and then what's going to happen? I'm going to see if you got this. So now the membrane is going back to rest. So you got your essay question, what would you tell me? The membrane's at rest now, which means what? What's keeping it at rest? The 3-to-2 ratio. So for every 2 potassium, that is going where? Good, inside the cell. Every 3 sodium will be going to the outside. That's your 3-to-2 ratio. And now the membrane is back at rest. What has to happen for an action potential to occur? The sodium-gated channels are going to, we have a stimulus. Sodium-gated channels are going to open up, and what's coming in? Sodium. We're going to have that influx of sodium. Then, at that point, that inside of that membrane is going to be more positive than the outside. And this all happens. The start of it all is with that local potential. That local potential is what starts the whole thing. Okay, a couple more things. We have refractory periods. And these refractory periods is what prevents an action potential from going backwards. Okay, that's why an action potential only goes in one direction. It's because of these refractory periods. I want you to know both of them. The first one is an absolute refractory period. It's a brief period during which a local area of the neuron's membrane resists restimulation, no matter how strong the stimulus. So during an absolute refractory period, I could burn 1,000,000 hamburgers, and we could have this room full of smoke. Remember, the smoke is the stimulus. But it will not, during this absolute refractory period, we will not have an action potential, no matter how strong that stimulus is. It won't happen. During a relative refractory period, it's a time which the membrane is repolarizing. Remember I said repolarizing, it's starting to relax again, right? So, and it's restoring the resting membrane potential. However, during this brief time, if the stimulus is strong enough, we can have an action potential. But it would have to be really strong. Good. I know this is a lot, guys. Give me some feedback though. How are you?
How you show us.
Mm-hmm.
And then you have the resting depolarization and the repolarization. So I like them.
Okay, good. Is it kind of sinking in a little bit, or you kind of?
I understand it better when you explain it instead of reading a slide, so that helps.
Okay, good. Okay, good. If I have time today, I could, try to find a really short video showing it to you. If not, that, you know what, I think the Amoeba Sisters has one. So you may wanna try that if I don't get a chance to do it, okay? But you're okay with this, right? And you see how, especially with the absolute refractory period, it will not allow, it won't allow it to go backwards. It can only go in one direction. Don't have to know this, but I wanted to give you an idea of how short these refractory periods are. So an absolute refractory period lasts approximately 0.5 milliseconds. It's not very long, right? But it's very important that we have that time to where we're not having any firing, okay? The relative refractory period is a few milliseconds after the absolute refractory period, during which the membrane responds only to a very strong stimulus. Okay, so please don't confuse the two, relative and absolute. And this is just showing you, during the absolute, we can have an action potential, and during the relative refractory period, we can, but the stimulus would have to be very, very strong. So at the peak of the action potential, the plasma membrane's polarity is now the reverse of the resting membrane potential. The reversal in polarity causes electrical current to flow between the site of the action potential and the adjacent regions of the membrane. This triggers voltage-gated sodium channels in the next segment to open. Thus, the cycle will continue producing conduction. This is a really nice visual too. So let's start number one at the very beginning. So what we have here is the refractory period. Here we're going to have the action potential. Depolarization during the action potential causes adjacent voltage gated sodium channels to open. And then all of this is the resting membrane potential. So then we come over here and we've got the refractory current, we've got the resting membrane potential, and we have the action potential right here. And then here, same thing, and we've got the action potential here, and then it just goes back to the beginning, and it just keeps, it's a continuous cycle. Okay, it just keeps going continuously. So as this cycle continues, producing wave-like conduction of the action potential from point to point along a nerve fiber. Adjacent regions of the membrane behind the action potential do not depolarize again because they are still in the refractory period. The action potential nerve moves backwards because of the refractory period. I'm sorry, never moves backwards. In myelinated fibers, action potentials in the membrane occur only at the nodes of Ranvier. This type of impulse conduction is called saltatory conduction. I want you to know that. So the speed of nerve conduction depends on the diameter and the presence or absence of the myelin sheath. You already know that, right? Because what's the myelin sheath do? What's the function of the myelin sheath? We talked about it Tuesday. Yeah, I'm sorry, you said?
Covers the axon.
Yeah, it covers the axon, and what's the potential? I mean, what's the action? I mean, function.
It sends nerve impulses deeper.
Yeah, well, it's going to allow for faster what? Nerve conduction. So here, what do we see? The speed of nerve conduction depends on that myelin sheath. That's why with MS, when that myelin sheath starts to become compromised, well, what happens? What happens to the patient? It starts out where they have coordination issues. I'm sorry? Yeah, misfires. And so what happens is things you want to think of it as this nerve conduction starts to slow down. In the beginning, the symptoms aren't too dramatic, but as the disease progresses, they're going to have more severe symptoms till eventually they're in a wheelchair because they can't walk. The fastest fibers, such as those that innervate the skeletal muscles, can conduct impulses up to 130 meters per second. That's close to 300 miles per hour. I just wanted to show you this to give you an idea of how fast these muscle fibers are, how fast that conduction is. The slowest fibers, such as those from sensory receptors in the skin, may conduct impulses only at about 0.5 meters per second, a little more than 1 mile per hour. Okay, just to give you an idea. Okay. You okay? I don't know about you, but I'm sweating. We're gonna take a little bit of a break, kind of absorb